Good afternoon, everybody. And in China, I have to say good evening because our speaker today is joining from China. In fact, he is a fellow South American, not Brazilian, but Argentinian. And our speaker today is Professor Marcelo Ciappina. He received his PhD from the Balseiro Institute, Argentina in 2005 and got a research professor degree from the Czech Academy of Sciences in 2019. And his academic training includes postdoctoral stays and senior positions in very renowned institutions from Germany, Singapore, USA, Spain, and Czech Republic. And at the moment, he is an associate professor at the Guangdong Technion Institute of Technology in Shanghai, China. And he's interested in attosecond science, atomic collisions. And we asked also our speakers, and some of them did, to send us some fun facts. So in his free time, he enjoys to listen to 80s music, loves to run and travel. At the moment, it's a bit tough for traveling. We can still listen to his music. And run depending on the restrictions in the area you're living. It is tricky, but I enjoy traveling, but at the moment we acknowledge that it's not that trivial. So Marcelo, thank you for joining. We really appreciate that you're going to give a talk, and he will talk about calibrating ultra-high laser intensities using ionization. So feel free to start. And we're going also to release a poll because since we're talking about 80s music, and this is kind of vague, we're going to release a poll and everybody's allowed to vote, panelists and everybody, but it's anonymous, about 80s music, which we are going to check. It seems that everybody votes, so I'm gonna end and share results. So we see that most like pop, you have some people who go for heavy metal. Have issues with the keyboards. Yes, okay. So Marcelo, feel free to start the talk.
Thank you, Carla, for inviting me to this interesting seminar sessions. So the idea today is to talk about the work we were doing trying to calibrate ultra-high laser intensities using ionization. So as you know, we can divide the laser intensities in at least 3 different regimes. So, and the idea is to try to find a method or try to export some method for the moderate intensities to the high and ultra-high intensities. So for moderate intensities, so typically what you can do is to measure the synchronization yield, the photoelectron spectra, or the high order Raman generation, and after use the semi-classical formula to infer the laser intensity as focus. When you start to increase intensity a little bit, you reach a problematic region where there are competitions between sequential and non-sequential ionization paths, and you can find the knee in the ionization yield. So this region is not so easy to manage. But if you increase the intensity even more, so you reach a regime where typically you can have multiple sequential ionization. So on the magnetic field driven recollision, there are many problems to solve here, but in principle, you can, as we will see, you can use multiple sequential ionization to characterize the laser intensity as focus. So the question is, if you have these intensities, in principle, the people claim that you did have in these several facilities around the world, here in China and Eli in Czech Republic, and probably also in US. So now we have the intensity regime we want to characterize. And the idea is to find a method or process to use and be able to characterize the intensity. So here you have some numbers. For example, here in China, the people claim that they are planning to build a 10 petawatt laser. So if you focus at the diffraction limit, typically you can get 10 to 23, but these numbers are theoretical. And in Eli, for example, they have 1 petawatt. So you can reach 10 to 22 watt per square centimeter. Also, some simple formula. So the idea is try to confirm these numbers with more precise measurements. There was an experiment a few years back claiming that you have measured 2 times 10 to 22 watt per square centimeter using a 300 terawatt laser at 1.1 hertz. But it is not clear that the focus you have indeed this intensity, because the estimation of this number was done using some low energy and low intensity and energy estimation. So the idea is try to, for example, validate these numbers and also find a method to be able to use for other facilities. So essentially, we want to confirm these intensity values, and we want to find strong field processes that can be used for the laser intensity measurement at focus. So we are aiming for a method that is straightforward, quantitatively precise, and unambiguous. So what we can use, there are several processes we can use. But for example, acceleration of ions and electrons, radiation reaction effects, radiation of probing particles, but all of them are really complicated and entangled together. But there is one, in principle, simple process, a strong field process, that we can use, and it's multiple ionization of atoms, typically heavy atoms. So here the idea is you put some neutral atom and you ionize from the neutral to the bare ion, for example, and from there we will see that if we are able to characterize the laser intensity. So essentially, this is very nice in principle because ionization is local in time, so and it's really non-linear. So essentially, if you move the intensity a very small amount, so you will see a big change in, for example, the ionization yield, and it's sensitive to the amplitude of the electromagnetic field, and there is not much sensitivity to the pulse direction and to the total energy. And as I say, it is highly nonlinear. This is what we want. So a small change in the intensity, we want to detect this change in a big signal. So let's see if we can use this multiple ionization to characterize the laser intensity at this intensity range. So there are further advantages from the theoretical viewpoint. So the theory is very simple. There are not approximations or few assumptions. And in principle, what you need to do is to detect ions, highly charged ions. But this seems to be not so easy indeed. So for us, from the theoretical viewpoint, it seems to be easy, but in the experiment, apparently it's not so. Okay, so the idea, first we need to be sure that we are working in a single electron process. So here the point is that we want to check that the electrons are ionized one after the other and there is no correlation between them. So if you put numbers together, so you can define the gamma parameter here. In the regime we are using, we are in the deep tunneling regime. So the gamma parameter is order of 10 to -3. And essentially one important parameter here is the characteristic field, that is a function of the ionization potential of the target. And also we are going to use the laser intensity the laser electric field in terms of 10 to 20 watt per square centimeter. So essentially what you can show is that if you define this reduces field, if this reduces field is much less than 1, so the process, this multiple ionization is sequential. The other point we need to check is that we are working in non-relativistic regime. This was surprising for me at the very beginning, because if you think this 10 to 20 or even larger intensities, so you can think that you are indeed working in a relativistic regime, but the tunneling, the first step of this process, is indeed non-relativistic, and it's still non-relativistic up to 10 to 26. So of course, once this electron is ionized, reach GeV kinetic energy, so there you need to treat this electron relativistically, but the first step, the step we are interested in, is non-relativistic. So this means that we can use the non-relativistic theory to model these ionization rates. So here the point is when this process remains non-relativistic when the ionization potential is much less than the rest mass of the electron. So 511 keV. So this means that you can use really highly charged ions without reaching this relativistic regime. So now we are sure that these electrons are ionized one by one, and we can use non-relativistic theory to model our problem. So what we will do is to use the ADK theory to model the ionization rate and write down a set of equations for the ionization of the neutral atom until the charge we want to model. So here you have some expression. So this is a typical exponential form of the ADK rate, and with different coefficients for the different initial states. And here you have the ionization potential, the reduced field, and so on. So essentially what we want to do first is to check what are the values of this reduced field in order to be sure that we are in the correct non-adiabatic regime. So if you put numbers here, you will see that for a full ionization, here this logarithm of series 1, this means that you fully ionize your atom. So the range of this reduced field is between 0.03 and 0.08 for different species. So essentially, we have chosen a number between these two and try to write down an analytical formula for the ionization as a function of this reduced field. So essentially, what we have found here is an universal curve that tells us the following. So if you want to characterize a given intensity, what you need to find is an atomic species with an ionization potential given by this IP star. For example, if you want to characterize 10 to 22, you need to find a species or ion with an ionization potential of the order of 7 kilo electron volt. So this is really interesting. This was done without doing any numerical calculation. So we will validate this in a moment. Essentially, so if you put the different ionization potential of different noble gases here, so you will see you can cover a certain range of intensities. For example, what this curve tells us is that if you want to measure, for example, of the order of 5, 10 to 22, so you need to use, you can use, for example, xenon 51 to characterize this point. Or if you want to use krypton, for example, krypton 35, so you can reach intensities that of the order of 10 to 23 or 2 10 to 23. So you can see that there are gaps here. So this is something we cannot avoid, because if you want to use noble gases, so you will have these gaps. But talking to some experimentalists, they say that in principle you can prepare some gas, some metals in gas phase or other materials. So in this way, you can cover a big range of laser intensity. So we have our approximated model. This is the most important formula here. The ionization potential as a function of the laser intensity. So this tells us which atom you need to use to characterize the laser intensity. So this is not new in principle because people have measured these highly charged ions. But the point is here, for example, it is not clear at all what are the quantity of or how many of these highly charged ions were measured. So in principle, you will need this information to characterize the laser intensity, or what you can do is check the intensity as soon as some particular species appear. For example, if you see or if you detect some particular highly charged ion, you can be sure that the intensity has reached this value. So we have here the experimental realization could be as follows. So you need to detect highly charged ions. So there are many prescriptions you need to fulfill. For example, we want that the laser pulse doesn't deform too much as travels through this gas phase target. So in principle, you need to use some particular pressure, but the problem is if you use this pressure, you won't have enough atoms to ionize. The other problem is it's difficult to produce highly charged ions, enough highly charged ions. So this means that you need to start from neutral atoms, and if you can imagine, for example, argon, so you will start from argon neutral till argon 17 or 18. So it means that you will have a change in many highly charged ions. This will be difficult to detect in principle, and from a theoretical viewpoint, you need to solve a large set of equations, but as you will see, this is not a big problem. And the final problem you have is, as you know, the focus has some shape. This means that the intensity is not constant at all. So it has some distribution, for example, the Gaussian shape. It means that in different region of the focus, you will have different intensity, means you will have different amount of these highly charged ions. So you need to find a way to put some slit or some device to collect ions in a very particular region. So this is an experimental problem in principle that could be solved. So what we have done is we have validated this approximated formula, solving some rate equation using the ADK theory. We have started from neutral, for example, and there are many paths that you need to write down. Also, this set of equations can be used for argon A plus or krypton 26 plus. So, but the good thing is that we have checked that there is no sensitivity to the initial state. So it means that you can start from neutral, or you can start from a different initial state. And the point is that at the end of the pulse, so you will have a particular highly charged ion independent of the initial state you have started. So this is very, very nice from a theoretical viewpoint, because you don't need to worry about the initial state of the system. So for example, here we have started from krypton 30 plus and model the different pathways using the ADK theory and solving this equation, so we can find, for example, as a function of time, the number of ions here. So this n is the number of the population of argon 14 plus, 15 plus, and so on. So as you can see here, doesn't matter where you start. So these curves are for different starting points, different starting species. At the end of the pulse, so you will have only argon 18 plus. So this is what is interesting about this method, that doesn't matter the initial state. So this is good also from the experimental viewpoint. So it means that you can put the neutral and detect only the highly charged, the highest charged ion, for example, and you will be sure that the intensity is a particular value. So another point is, as we have checked that the laser, so this ionization process is really non-linear. So it means that if you change the intensity a little bit, so the ionization yield will change dramatically. So as you can see here, it's almost a step. And in this case, so we have validated using a numerical calculation this approximated formula. For example, for argon 16 plus, so we have checked the appearance of this ion is this value in really good agreement with the approximated value. This means that if you don't need to solve this numerical set of equation, you can use this approximated formula to at least to design the experiment. So once you have designed the experiment, after you can validate if you want with the numerical calculation. So another thing you can do once you do the focal averaging, so we have done the focal averaging using a Gaussian shape laser pulse in space. What you can do here is, for example, to characterize the intensity is to measure the ratios between different species. For example, from this, I think it's krypton 29 to krypton 35. For example, measuring the ratio between these two species, following this curve, you can be sure that the intensity you have is this 10 to 24. So there are two ways to characterize the intensity. In principle, the appearance of a highly charged ion, and the second one, more precise, but probably more difficult to do experimentally, is measuring the ratios between different species. So if you can detect a set of a species, a range, so measuring the ratio between them, so you can characterize the intensity much better than the previous case. So essentially, so we have presented a method able to characterize the laser intensity at focus. So in principle, numerically, it's not so complicated to implement. The accuracy is really nice for the interval of intensities which are densely covered for ionic state. So as you have seen in the universal curve, there are certain regions where you don't have a species to put. So there are no intensity limitations, so you can go further in intensity. For example, you can use relativistic theory if you want. If in the future the people plan a facility for 100 petawatt laser or something like that, so you can use in principle this method. So we have validated this approximated theory using a full two-electron theory. Also, we have corrected, for example, you can think that for these highly charged ions at this gamma Keldysh parameter so low, so we are in some cases over the barrier ionization, so we have corrected this. The changes are relatively small. And we have also checked different focal geometries. So this is important because in principle, you need to include this, the focal shape and in the theory, because you have this distribution of intensities. So we have checked different, in principle, we can put any focal shape and can do calculations. So the problems, of course, the life is not so simple as it could be. So there are these intensities, gaps in the intensities. This could be a problem because maybe your design is only able to generate some intensity where you don't have gas phase ion to put inside. So, and there are, as you need to put the neutral, so the problem is maybe you need to design the detector in a way that all the low charge ions are discarded. And this could be also a problem. So maybe your detector saturate with low charge state that are not interesting for the laser intensity measurement. But the ions you want to detect highly charged at once, so are not measured. So, and the final question is up to now. So there was a recent paper in Optica of South Korea claiming that they have measured, or have estimated in a very precise estimation, 10 to 20 or even larger intensity. So this method in principle should be able to validate in a very precise way. So these ultra high intensities. So here you have some set of references. The first one is about the presentation of the method after we have done the over barrier correction. So we have put these focal shape effects in different focal shapes in the theory. And finally, we have validated this ADK theory using a fully correlated theory for 2 electron ions. So we have validated this ADK yields, ionization rates. So let me thank finally the organizer of this seminar, so Cornelia, Abby, and Carla. It was an amazing show, and also my collaborators and people who was working in this project. So thank you very much. And I'll be happy to answer questions and discuss. If you have some ideas or some suggestion, it will be very interesting to hear. Thank you.
So thank you, Marcelo, for your nice talk. Now, please feel free to raise your hand or put your question in the Q&A session. And also before we start, I would like, sorry?
No, how I can see, okay, so you will transfer me the question, or I can, if someone speak, I can, yeah.
Yes, and before we start, I would like to advertise that we have a special issue associated with the workshop Quantum Battles in Atto Science and Atto Fridays. And this is a special issue, Quantum Aspects of Atto Science in the European Physical Journal D. And thank you so much for all of you who have already submitted, but we are still waiting submissions. So if you would like to submit an article, feel free to do so. Deadline is the end of this month, but let us know if you need more time or how things are going. And now, are there questions, comments? I mean, one question would be, with regards to this calibration and with regard to this intensity, and it is something which you mentioned, which is related to the ADK rate that you are using. How accurate is this? And in what regimes can you still use it? Because I would expect this to work for the low frequency regime, but at some point it becomes a bit dodgy, right? Or even
no, I mean, yes, the laser, I mean, we are using some parameters from ELI, so it's 1 micron, and intensities about 10 to 20. So these are our lower limit, I would say. So, and for, I would say if you start from neutral, so there are some problems with ADK, but as soon as you ionize, you have 2 electron ions. The ADK, we have compared the ADK rate with the fully correlated calculation, and it works very nice. But in the middle, there are some problems. Yeah, you're right. But here, in principle, when you put the neutral, you ionize very quickly. But yes, you're right. So the ADK is not so precise when you when you have low charge ions, I would say.
There is one question from Andrew Maxwell. Hi, Marcelo, really nice talk. Interesting to hear the tunneling rate formula is valid until 10 to the 26 watts per centimeter square. Is for a specific wavelength, and how would this vary as you change the wavelength, which ties again in this previous one?
It's a good question. I don't know. We have checked for 1 micron, but yes, it would be interesting to check for other parameters. So yeah, because we have used typical wavelength for these big facilities, but if you change the wavelength, I don't know. So yeah, I would expect that it works, but I'm not sure. So you need to check that this the tunneling. I mean, here we are with gammas 10 to -3 or even smaller, or with these highly charged ions. Maybe if you change the wavelength with these highly charged ions, the ADK works. But yeah, it's a good question.
Any further questions, or would you like to follow up on this?
Yes. Please give me one experimentalist who able to give some hints about this. Would be nice. I mean, I think the main problem
who has raised his hand.
I mean, the thing, the main problem here is the implementation of this of a setup to test this method.
So we have here Francisco, who has raised his hand. So please feel free to ask your questions or make any comments if you would like to.
Yeah. Well, thank you for the excellent talk, Marcelo. And I just wanted to ask. So apart from the characterization of the lasers, are there being like new experiments being carried with these lasers, or the experimentalists are waiting until the full characterization of the laser is completed?
No, I mean no. The point is one of the problems if you promise some intensity, or if you say I have this intensity, so you are not sure that this intensity is in the focus. So I think one first experiment the people should do before to go into more complicated stuff would be, okay, let's try to find a method to be sure that the intensity like we promise is the one we have. But okay, in principle, they can do other experiments, putting solids and something like that. But the problem is maybe if you don't know the intensity, you are expecting something that you won't see. So this could be for me important, at least to try to check that the intensity of the order of magnitude at least, or with some degree of accuracy. Okay. No, yeah, the experiment. I mean, the experiment will be in different paths. So, but this could be one experiment, probably.
Okay, and what's the maximum intensity that has been tested at Eli?
No, I mean, no, there is no test. I mean, they are finishing the implementation. I mean, the commission. So the big laser is still not under operation.
Oh, okay.
They are finishing. Yeah, they are finishing the transport and So I think one of the problems is the focus, the mirror to focus the laser. So this is one of the challenge. How you focus this 1 petawatt to 1 micron. So it's not so easy.
Okay. And from the design of the laser itself, it's not possible to predict either, or you.
This is what the people do is you don't put the full intensity. So what you do is you do a measurement, I mean, of the geometry of the shape and some energy measurement at low intensity, and after you scale up. But this is, I mean, no, you are not measuring at the real intensity.
Okay.
These are the estimation I show. So the people do some low intensity estimation, and after say, okay, if I put this energy, I will have this intensity, but they don't measure the high intensity.
Okay.
This could be a method, a possible method to be sure that the intensity you promise is the one you have. Yeah.
Okay.
Thank you. Thank you.
We have another question from Akanksha Dubey. It was a really nice question. I would like to know, you mentioned that until 10 to the 24 watts per centimeter square, things can be treated non-relativistically. So in which regime do relativistic things come into picture?
Okay, yeah. I mean, tunneling remains non-relativistic till 10 to 26. So the tunneling step only, yeah? This is the point. So the tunneling step, you can treat non-relativistic. The rest of the process, of course, are relativistic. So you can, yeah. So in principle, for the tunneling step, so you can use this formula. If not, you need to revise the formula, but I think you cannot reach 10 to 26 with the current experimental setup. So I think the maximum they are planning is 10 to 24 or something. So for the tunneling step, so you can safely use this method. Of course, if you want to calculate the energy or the velocity or the dynamic of the electron after tunneling, yeah, you need to use full relativistic theory. Yeah, but the tunneling step is okay treating non-relativistic. Yeah.
And she has another question, which is another point that she would like to ask is, in the adiabatic approximation, electron-electron correlation is not considered. What are the effects if it is considered?
This is your question. So for this intensity, we had checked for two electrons. I mean, the point is everything happened. So you suddenly get the fully ionized atom here. So there is I think no time to have this correlation effect because all the electrons go very quickly to the continuum. But we have checked the correlation for two electrons. At this, remember that we are in intensities 10 to 20 and above. So for this intensity, there is no correlation effect. But of course, if you start to decrease the intensity, I imagine that you will have this recollision, all this effect you have seen at lower intensity, because here you are with this highly charged ion. But for two electron ion, for example, there is no problem. So we have checked the ADK formula and it works very nice compared with a fully correlated calculation. So yeah.
Okay, so hello, can you hear me?
Yes.
Yeah. So my question is that actually, So actually, in photoionization studies, people consider this relativistic random phase approximation. So in that, actually, they takes care of this electron-electron correlation. And so from that perspective, I wanted to know, because in that actually they take into account this interchannel coupling kind of thing. So in that also actually one electron get scattered off of the neutral atom and it gets ionized after that. So I just wanted to know, like, what are the kind of effects if electron-electron correlation is taken, and in which conditions actually it is not considered here, because in that case now, if you see, it is actually considered. So that was my point, like in that photoionization work, and it is of course like so from that perspective, I just wanted to relate, because there they takes into account these things. So.
Yeah, for two electron ions, we have checked this correlation and doesn't play. But I agree with you. If you reduce intensity a little bit, and you have this highly charged ion, 3-4 electron, maybe you have some effect. Yeah, true. maybe, yeah, probably you will, because this
So
knee,
in
you
their
can
case,
scale this knee, yeah. Yeah, you can
yeah, so in
scale
their
the
case
knee.
they, yeah, so in their case they study rare gas atoms actually. So there also they go till like 100 ev also, sorry, 1000 ev also. So I guess there also the kind of like electron energy is high, like 1000 ev above. So I just wanted to know, like since one electron is knocking out from the like entire atom, so that already has some sort of this correlation with the like what it is living. So from that perspective, I was just thinking, nothing else.
Yeah, because you know, this knee, so when you change I mean, this knee, you can scale up with intensity, of course. You can see some people have seen knee with different ions, yeah. But here we are very far from this intensity, yeah. But I agree. So if you reduce a bit intensity and you use these ions, you will see some effect, yeah.
Okay, okay, thank you very much. Yeah,
Thank you. Thank you.
yeah, it was a nice talk. Yeah, thank you.
Thank you. There are further questions. Anybody has comments? Would anyone like to say anything? We're going to stop the streaming soon, so if you want to ask anything off record to Marcelo, you will have the opportunity. So there is one more question. Another question from Andrew Maxwell is to deal with focal averaging.
Yeah.
Intensity shells in the experiment by taking the difference between two close but different intensities. This could remove the effects at lower intensities from focal volume.
Yes, I think this is a very good question. I think one of the ideas is just to put a slit. Yeah, I mean to do a time of flight in terms of one slit. So a small slit close to the focus, and to avoid these shape effects. Yeah, as Andy said, theoretically, so you can do in principle this experimentally. So you take a shell only of this laser focus, but I don't know how easy it is to do this in the experiment. Yeah, you're right. So the idea is just not to collect in the whole focus, just to do some kind of slit. But the problem you have is you will have probably not so much ions. I mean, this is a question. Yeah. Maybe an experimentalist can answer. But yeah, this is a good point. So to avoid this many intensity distribution, so what you need to do is to try to catch only a small shell or small slit. Yeah, this could be an idea to implement. Yeah.
Can you hear me? Okay.
Yeah, can you hear me?
Yeah. Okay. Cool. So, do you think at these kind of intensities you'll get quite a lot of ions anyway, right? Like.
No, this is a good point. I don't know, because these are 1 hertz. I mean, it's 1 shot per second. And if you don't want this plasma, not too much plasma to
Okay.
degrade because the problem when you have too much ionization, the laser deforms, no? And I mean, you need to find a compromise.
Yeah, that's a pretty low repetition rate.
So yeah, the repetition is a problem because you have one. I mean, probably you need to do this measurement in 1 shot. And and if you put this slit and you do, maybe you cannot collect so many ions. But maybe if you can collect at least a few ions with a charge, with the adequate charge, maybe it's enough to say, okay, if I measure these ions, my intensity is of the order of something. Yeah, this could be.
Okay.
Yeah.
Thank you.
Good idea. Thank you.
So are there more questions, comments? Would anybody like to say anything? If you would like to say something, but YouTube is too much for you, we're stopping the streaming and the recording pretty soon. And if you would like to talk to the speaker, hang in there, and you have the opportunity to do this pretty soon. So people who are watching on YouTube, thank you for joining, and thank you for your support. See you next time.